deeply about Nyquist Criterion and its implementations. So basically, while designing a system, a negative feedback system or a negative feedback amplifier, we already make sure that G block and H block does not have any poles, as these blocks are built independently. So we can say that the design of the loop gain GH itself to be stable and then make a negative feedback system. So we are aware about the transfer function, and yes, we can assume that GS HS can does not have any right hand part poles. So basically the G block and the H block are stable within themselves. So what we do is now we evaluate G of S, H of S starting from 0 to infinity and plot its imaginary versus real parts and mark the point -1, 0, which is basically a critical point. So we have our G of S, H of S function and its uh, S plane. So from S in the S plane, we go from S equals to J0 to S equals to J infinity. And then when we evaluate G of S, H of S on the imaginary axis, so its imaginary part and its real part are plotted on y and x axis. So basically, this is Sj equals to 0 and it goes from here to S equals to J infinity, and this curve is for positive frequencies, and this is where our -1, 0 point lies, and this is our Nyquist plot. So similarly, for negative frequencies, we evaluate g of s, h of s for j minus infinity to j0 and plot the imaginary versus real parts. So this is a plot of imaginary versus real part of our loop function, which is evaluated from j minus infinity to j0, and basically starting from s equals to j0 to s equals to j infinity. So this is our Nyquist plot, and here lies our critical point. So the Nyquist criterion simply states that for g of s, h of s not having right-hand poles, which is already pre-considered and taken care of. So basically, when in a complete negative feedback system, the number of right-hand poles, or rather right-hand part zeros of the function 1 plus gh, which corresponds to right-hand part poles of a total function of negative feedback amplifier g by 1 plus gh, is equal to the number of clockwise encirclements of g of j omega h of j omega to the point -1, 0. So uh, basically g of j omega h of j omega is in the plot of imaginary versus real part of function g of j omega h of j omega. So this is what we are talking about. So let's take an example. So in this example, we'll start from j minus infinity to j0 to j infinity. So from negative frequencies minus infinity to positive frequencies infinity. So uh, we have the uh, g of j omega, h of j omega imaginary part and its real part, and the plot looks something like this. So and it encircles the critical point 2 times. So we can say from this plot that we have 2 times encircled the point, critical point, and therefore our negative feedback uh, amplifier or its transfer function has 2 poles in its right hand plane, and thus the system is unstable. Now this is just for the sake of example. So let's say now our amplifier design does not only need stability but also a good behavior, meaning we need less ringing. So let's look at Nyquist plot for something uh, for which we can calculate the result analytically. For example, for ideal delay case or second order case, and then let's extend it to all other cases in general form. So let's take our case one where there is no delay and no pole. So we know the loop gain, which is basically g of s h of s, is omega u by ks. So in this function, there is only one parameter which is going to be changed, and that is omega u. So we know that we have only one parameter, and which and even if we change it, we will be on j omega axis only when we plot the uh, imaginary versus real parts of the function L of s, which is our loop gain function. So we know that the curve basically this point, this point, and this point is same, so it is connected like this, and our curve goes from s0 to sj0 to sj infinity and sj0 to sj minus infinity. So this curve will never going to encircle this critical point, and thus the system with no pole or no delay is unconditionally stable. Now let's go to our case number 2, where there is one pole and we know the delay function of one pole. So our loop gain function will be omega u by k divided by s times 1 by 1 plus s by p2. So this is our transfer function. When we take its magnitude, this is our magnitude, and the phase shift is basically minus pi by 2, which is introduced itself by the integrator itself, and by the pole introduced is minus tan inverse omega by p2. So when we again plot the Nyquist plot or the Nyquist curve, basically imaginary part of the function and real part of the function, and then we state that when we look at our phase of our function, so the phase lag is this particular angle from here to here for our positive frequencies. So let's consider first the positive frequencies, and the phase lag is from here to here, and now we know that this pi by 2 is constant, and this part of the phase will lag maximum up to minus pi. So the curve for the positive frequencies will always stay below the negative real axis, as the maximum lag or the maximum phase it can give is minus pi. So we can say that even if we can change the parameters of the function over here, any of the parameter of the function, even if they are changed, and still there is no chance of getting encirclements at the critical point, as all the uh, twist lies in the phase and it cannot go above the negative real axis. So we can say that this system is also unconditionally stable, as this is not encircling the critical point. Now let's take our case number 3. In our case number 3, we have got two poles. So let's say two identical poles at P2, and this is how our transfer function will look like. So omega u by k divided by s times the transfer function of two poles at P2. So it's obvious that the magnitude of LFS keeps decreasing with omega. So basically this is how the magnitude is, and uh, coming to the phase, so the phase shift minus pi by 2 again is introduced by the integrator itself, and by the pole the phase shift is minus 2 tan inverse omega by p2. As we know, every pole contributes of a phase shift of, or a time delay basically, of 1 by p2. So at very large frequencies, let's say omega equals to infinity, the maximum contributed phase shift is minus 3 pi by 2. So what it corresponds is basically, let's look at the Nyquist plot. So while looking at the Nyquist plot, so now we can see the angle can go up to minus 3 pi by 2. So what we can say is we have our equation for our phase lag, and for lower values of P2 the phase is increased. So we can say if this is a plot of a P2 where there is a certain frequency, and now if the value of P2 is lower, So the plot will somewhat look like this, starting from Sj0, and this is how the plot will look. So we can say that for lower values of P2, the angle will increase, and as smaller values of P2 means larger value of parasitic delay, which is 1 by P2, eventually the system tends to be unstable. So we know from our previous analysis, P2 is equals to half of omega loop. Therefore, the pole lies on imaginary axis, and this is our boundary condition. And when P2 becomes less than half of omega loop, then the poles are in right-hand plane. So the critical point the critical point can either lie inside the encirclement or outside the encirclement, depend upon what value of P2 we are taking and what curve are we getting. So this system is basically conditionally stable. Now let's say these two poles are not identical. So in that condition, let's take a case where with two non-identical poles at P2 and P3. So similarly, our phase will look like this. This is contributed by our integrator. This is contributed by P2, and this is contributed by P3. So basically, and the magnitude is basically omega u by k divided by omega 1 upon 1 plus omega by P2 into 1 upon 1 plus omega by P3. So for very high values of omega, again, this part will contribute to minus pi by 2. This part will contribute minus pi by 2. And in total average, overall lag is minus 3 pi by 2, and which is same as this condition. So even with two non-identical poles, the system is conditionally stable based on what value of P2 we are getting. So let's take a case 4 when we have more poles, let's say 3 poles. So this is how our transfer function will look like. This is its magnitude, and this is its phase. So this states that the possibility of encircling the point, the minus 1 comma 0, which is basically a critical point, as a total phase can be minus 2 pi at very large omega. So let's say the maximum phase lag which can be contributed is basically minus 2 pi. So for systems having two or more poles, there is unconditional stability based on what value of P we get. So this is how Nyquist rate or Nyquist criterion tells us about the instability. But now again, for a good amplifier design, we also need very limited ringing. So let's take a system with one pole at P2. So this is how it looks, and this is its Nyquist plot. So now we know the transfer function looks like this, and the phase is this. So as P2 decreases, the phase increases, and we know how it does. We have analyzed already, and the phase comes closer to the negative real axis. So we know if, let's say, this is our plot of P2, and if it decreases, so our plot comes more closer to negative real axis. And to analyze it properly, what we do is we draw a unit circle which basically passes through the point minus 1 comma 0, which is our critical point. And if the curve of the loop gain comes closer to minus 1 comma 0, ringing happens. And now let's look what phase margin is. So basically the point where the unit circle and the plot cuts each other, and how far is that point? It's from negative real axis in terms of angle is called phase margin. So the angle, so basically phase margin signifies how safe we are or how far we are from the critical point. So let's redefine the phase margin again. So phase margin is nothing but the angle between negative real axis and the point of intersection of Nyquist plot and unity circle. So we know for critical damping, P is equals to 4 times omega u by k, and if P becomes lesser than 4 times omega u by k, then ringing occurs. So I think I have made a nice effort to explain phase margin or definition of phase margin. So basically it signifies how safe we are or how far we are from -1, 0, and how nicely we are able to avoid ringing. So now we will calculate the phase margin for a critically damped case in second order system. So in second order system, like we know, P2 is equals to 4 times omega u by k, and the transfer function of second order system with one pole is this. So in mathematical terms, when Nyquist plot intersects with the unit circle, so somewhat this points. So to represent it in mathematical terms, so the magnitude of loop gain becomes 1 and phase margin is nothing but the phase of loop gain at which the loop gain, magnitude of loop gain is 1 plus pi degrees because it is calculated from negative real axis. So this is the mathematical mathematically showing how the Nyquist plot intersection with the unit circle looks like. So now let's come to magnitude of L, and instead of saying that when magnitude of L is equals to 1, let's take a simpler case. So when we calculate a magnitude of L at S equals to J omega u by K. So we'll take the frequency omega as omega u by K, and we'll just put it in the transfer function and take its magnitude. So we will come to a conclusion that the value is somewhat 1 upon under root 1 plus 1 by 16, which is basically close to 1. So we can say that the mod of L becomes 1 when omega is nearly equal to omega u by k. So now let's see the angle of loop gain or the phase of loop gain when S equals to J omega u by k, which is equals to minus pi by 2 contributed by the integrator and contributed by pole, where our omega is omega u by k. So when we can calculate this, so after calculation, so we will get minus pi by 2 minus tan inverse 1 by 4, and we know that phase margin is nothing but pi plus angle or phase of loop gain at S equals to J omega, and here omega is omega u by k, and therefore our phase margin comes to be 76 degrees. So if we apply this phase margin to all higher order system, it turns out to be that they will also become well behaved. So I think this is how we lay an idea of Nyquist criterion in designing of negative feedback amplifier. And now in further videos, let's discuss more implementations of Nyquist rate, or rather phase margin. That's all for this video. Thank you so much.